I would like to speak about this farming in space, starting by the fundamentals, is what do we need to keep the astronaut alive? So he will need oxygen, he will need water, and he will need food. And if you make the calculation of this for a mission to Mars for 6 crew members, you will be, with a bit of hygiene, above 100 tons. So it's a huge quantity. It's really a lot. But, surprisingly enough, he produced more or less the same quantity of waste. So from this, you have two options. Either you do bigger launchers, as we have done already, which is a real success. Either you try a most modest European approach. You try to recycle everything you can. Yeah? So the challenge is, in fact, can we, with technology, assemble technology in order to be able to transform all the waste produced by the mission in oxygen, water, and food? And this has to be done, of course, with a minimum of mass, a minimum of energy, very safe, crew time, and very robust. How does it work here on Earth? Because here I benefit of oxygen, I benefit of water, and I benefit of food. Yeah? What is the technology which is behind this, who works quite well? In fact, it is our ecosystem. Yeah? So, of course, we are not trying to fly a lake. It will be a huge mass, it will be very big, and it's too complex, not robust enough. But if we look at the different level of an ecosystem, you realize that you have several functions. You progressively transform the waste in order to produce oxygen, water, and food. It's almost by layer if you look at the lake. So 30 years ago, European scientists and engineers thought that if we managed to copy or to be inspired by a terrestrial ecosystem, we could participate to a Mars mission. Yeah? So this is exactly the concept of MELISA. You find here in this loop, in this closed loop system, the different layer of the lake, starting from the bottom part of the lake, and progressively transforming all the waste in the nutrients to be able to produce plant and algae, and the plant and the algae will produce the oxygen by photosynthesis, produce the water by perspiration, and produce the food. So we try, and we, let's say, assemble as well a community of engineers, chemists, scientists, space engineers, all together in order to be able to develop this system. And now I would like to show you how engineers see an ecosystem. It is exactly the same, but at any time of the recycling, we are able to know how we are in carbon, in nitrogen, and more or less all the Mendeleev table. So that's really the challenge. So it's a project we started 30 years ago, with today around 100 engineers, scientists, mathematicians, chemists, cooks, philosophers, sociologues. I mean, it's really a rather big community, around 14 to 15 countries in Europe, so it's not a small activities. And we have already created 3 spin-off companies. We have a foundation for education, and we have already fly 9 experiments on board space station. So how do we finance MELISA? So from the beginning, we did it in total collaboration with terrestrial interests, because we are convinced that this has a lot of terrestrial interests as well in terms of environment, sustainability, circular economy. So I don't know if you are familiar with what we call the TRL, which is a degree of progressing of the technology, but more or less between TRL1 and TRL5, it's the same technology for terrestrial application or for space. And this is why MELISA is more or less co-funded by 50% of terrestrial industry. And you see on this graph the different level of participation, starting by academic, up to the space industry if we want to go to space, terrestrial industry if we want to go on ground. So here is an image of the community of MELISA, and this is how we do it. We started in the academic world, really basic research, low TRL, then progressively we go to pilot. Yeah? This is really starting to be very continuous process for years. This one is running for the last 3 years. Yeah? And then we go very small, we test it on board station, generally on board station. So it's the same function, but with a much smaller scale, where we will be able to test our technology to see if it works in microgravity. And then, when we have validated this technology in space, then we are able to size the complete system. You really need to go to all these steps in order to size your system. So we have a pilot plant, which is, by the way, in Spain, in Barcelona, where we are progressing assembly all the process. We have already demonstrated the oxygen CO2 recycle with animals for more than 6 months. Now we are collecting urine as well as a step before the algae and the plant. We are doing tests in Concordia, in Antarctic. For the last 12 years, this base is fully depending on the water recycling system. So it's very good in terms of operation. We know exactly where are the weaknesses. I mean, 12 years, this base is absolutely not accessible during winter. It's around -80 outside. Plane cannot go, so this gives you an idea of the challenge. And we have as well bed rest. I mean, you have understood from the astronaut, and when they are in microgravity, the human physiology is different. So recipes that you like maybe on Earth, you don't like them in space. So you need to be able to test your recipes in conditions which are a bit similar of microgravity. But of course, you have a limited number of raw products. Yeah? In the case of Melissa, in this case of this experiment, we had only 8 plants. So we challenge a few cooks. By the way, we challenge a French cook, and a French cook which is very well known in Dubai, Mr. Alain Ducasse, who has his restaurant here as well, in order to elaborate a certain number of recipes and test them during, in this case, for 3 months, where we had this volunteer, head down, which simulates the body behavior in microgravity. The fluid shift is completely different, so you can have a different perception of the salt, sugar, and fibers, and so on. And this is a test we perform. Today, on board the space station, we have the Artemis experiment, where we demonstrate the recycling from CO2 to oxygen. This has been running for the last 6 months. And breaking news today, I can tell you that the kinetics of microalgae in microgravity or on Earth is exactly the same. There is no difference at all. The prediction we had is perfectly perfect. It's exactly the same thing. Now, of course, we have to understand for multi-generation. That's why we are waiting for the biomass sample, where we will study transchromic, genetic, potential effect of radiation. But this is working very well so far. So I would like to end by a STEM activity that we have started. 3 years ago, we did a STEM activity in Europe with 1,000 schools devoted to microalgae. It was a full success. And now we are trying to do a bit better. In fact, we would like to involve the European community, open to the rest of the world. If you want to participate, it's fully open, in plant characterization. You know that there is thousands and thousands of plants. We don't know today which one will be the best adapted to Mars or to another planet situation. And if we do it only in linear, one by one, with only one space agency or one lab, it will take us centuries, and everybody will be already arrived in Mars before we are finished. So that's why we would like to do it in parallel. And with a kit which is standard for everybody, we will be able, with an apps on phone, to model with big data, data management, be able to model the morphology of the plant development. And on this, I will pass the microphone to my colleagues.
Okay, hello. My name is Julio. I am from Peru, so I'm very happy to be here, far away from my house, from home. Okay, I am a researcher in this project. This project is Potatoes on Mars, and sound a little a movie, right? Like a movie, but it's not only fiction. It's a reality. It's reality. So this is the picture of of the critical requirements for productive agriculture. No? There are several talks about this: the water and energy, power. But the objective in this project is basically 2 variables, two requirements. One is plants or vegetables, the candidates to grow outside, and soil. Soil maybe is the most abundant in situ resource in the asteroid, planet, or moon. So we have to use the soil. Obviously, there are other options. There are other options without soil, but this is not the objective in this project. We have to look for what is the best candidate that can adapt to extreme conditions. And the other thing is understand what is the limit of plants, of the plant growth. In case of the soil, we need to understand what is the extreme natural soil's properties, because we need to understand what is the interaction between molecules and bacteria in the soil to look for if these bacteria can help to the vegetable to grow. After, if we understand better these variables, we have to use new technologies to improve it. We can improve, for example, soil using nanotechnology, nanoparticles, for example, that attract salt or oxidants in other planets. And in the case of the vegetables, we can use biotechnology, trying to improve these limits of growth. At the same time, if we understand better this landscape, we are improving the power consumed as well. This is the different phases of this project, and the final obviously is try to send a robotic mission if all of this is successful. Why Mars? The question is why Mars? Because Mars, there is a lot of evidence of water in the past, a lot of evidence of water in the present. It's frozen water, but maybe it's liquid water as well. Liquid water is salty due to the presence of perchlorate, this type of soil, this type of salts. But there are good evidence showing that during some seasons, Mars, maybe the liquid water is present. The other important thing to talk here is about the lessons of Martian-like soils. We have different environments around our planet that mimic some characteristics expected on Mars. And the different researchers you can choose different, for example, characteristic or chemical characteristics, or physical, mechanical, or geological, and you can use what is the more properly analog to use, depending on what experiment you want to do. In this case, I am using the La Jolla analog marine soil in La Jolla. La Jolla is located in southern Peru, as the north part of the Atacama Desert. This Mars-like soil is really interesting because this area first is hyperarid, and the more important thing is the content of organics is the lowest content, the lowest level by far. So this is including lower than Atacama Desert. So it's really important, this place. And this soil contains a lot of oxidants as well, and volcanic minerals like Mars. We need food, but it's very expensive to build this habitat. And obviously, we need real food, not dehydrated food, not synthetic food. We need real food, and this is one need. So, looking for the candidates, we have chosen the potato. But why potato? Why potato? In Peru, we have 4,500 varieties of potatoes, so you can eat different colors, on different tastes of potatoes, or fast food. There is different potatoes with different salts. So it's amazing the amount of potatoes we have. But the phase one of this project is look for the super potato. What potato can resist? Now this is a picture of the market with different types of potatoes. So the phase wouldn't be at the same time. We needed a Martian soil. So we take 800 kilograms of this Martian soil from La Jolla and take them to the International Potato Center in Lima, Peru, to do this experiment. So after 1 year of experiments, comparing the soils, the Mars-like soils, with normal soils, and this is a logo, the project with NASA Ames. We use 65 varieties of potatoes. This is the different potatoes used. The details of these varieties are in the paper, in International Journal of Astrobiology. It's a recent paper. And you can see that. But we started in October, November 2016. We, 40 varieties of these experiments grew and formed the plant, but not the tuber. So only 4 varieties were able to form tubers in these experiments. They are these experiments. So this index of select genotypes, for example, indicate the values of chlorophyll in the leaves. So this is really lower values comparing to the normal soil. But this is the varieties, the genotypes, that they are on the super potatoes. After 1 year of experiments, we found the super potatoes. So this picture shows the fresh tuber yield, the product, the grains is maybe 6 grains, small potatoes. But in the new experiments, the yield is basically the double, 12 and 15 grams of potatoes. And the graph on the right is a percentage of the tuber yield, is comparing Martian soil and standard soil. You can see the four super potatoes show basically 10% of the size of the normal potato. So it's small potatoes, but they are preliminary results, right? And the phase 1C, at the same time, we needed to build a bioreactor, no, to grow the potato in extreme conditions, mimic the Martian conditions, or lower than Mars, not Mars, but extreme conditions, no? It's very important to regulate and set up what conditions we need to evaluate, to analyze. So the more important thing here is this simulator was built for students, entirely for students, were designed, programmed, completely digitalized and programmed by students. That's really important, no? This is the pictures during the construction of this simulator. This is the pump, or the vacuum pump, the freezer, the mix, the different type of gases, trying to mimic the atmosphere on Mars. So this is a prototype, no, built entirely for the university, in the university. And the phase 2 was to determine the limits of potato growth. So in this case, we are comparing Mars simulator and phase 2 experiments. Basically, previous limits published for potato growth was 1% of CO2, 500 millibar, soil with 4% of salts. But we exceed these results. With this soil, this potato receives 40% of salts and 10% of CO2, so it's really important to remark here. So it's a real super potato. This is the video, if you want to see the growth of this potato. Why do we need to take potatoes to Mars? We need fast food in Mars. no? But the real objective is the certification of global warming, and a lot of new places, no, are very difficult to culture, to sow different plants. So it's important this technology help and is useful to improve that. So we are living in the future right now. Phase 3 is improve these limits, and phase 4 is maybe send a mission, a previous mission, a robotic mission. And we are living in an extraordinary moment. All the people are come together to face the same challenges, so it's really important in this type of project. Thank you.